You know that coffee mug on your desk? Or the tiles on your kitchen floor? They feel, well, pretty simple, right? Just solid objects. But if you could zoom in, way, way down to the atomic level, you'd find a secret world, a hidden universe of unbelievable architecture. Today, we're going to pull back the curtain on that secret world and find out what really gives ceramics their incredible properties.
So, what is it that gives a material its unique superpowers? What makes one thing super strong, another magnetic, and another one brittle? Is it really just about the chemical ingredients you toss into the mix, or is something else going on? Well, it turns out the answer is so much cooler than that. It's not just what's inside, it's how that stuff is organized. The arrangement. That's everything.
And when it comes to organization at the atomic level, you basically get two choices. You either have complete and total chaos, or you have perfect repeating order. And that single difference, order versus chaos, is like a master switch that controls pretty much everything about that material.
And you can really see that contrast here. On one side, we have crystalline materials. Look at that. It's a perfect repeating pattern, like soldiers standing in perfect formation. Then, on the other side, you have amorphous materials, which are just a total jumble, a chaotic mess, like a huge crowd of people milling around. And it's that predictable, perfect order in crystalline materials that is the secret to so many of their powers.
Okay, so if a crystal is this super organized structure, what's it actually built from? I mean, think about it. A brick wall is built from thousands of identical bricks, right? Well, a crystal is built from one tiny repeating pattern, a little blueprint. So let's meet that fundamental building block.
So before we get to the blueprint itself, we have to imagine the scaffolding that it's built on. Scientists call this the crystal lattice. Now, this isn't a real physical thing. It's more like an imaginary 3D grid, a set of points in space that shows exactly where all the atoms are supposed to go.
A really good way to think about the lattice is to picture the grid lines on a piece of graph paper. The lines themselves aren't the drawing, but they provide the structure, the exact locations for everything you're going to draw. That's what the lattice does for atoms.
So if the lattice is the grid, then the unit cell is the smallest little piece of the pattern you can just copy and paste over and over again to create the whole thing. This is the absolute fundamental atomic blueprint of the material.
Here's another way to see it. That larger grid on the right, that's the whole building, right? And that little highlighted box on the left, that's the single identical room, the unit cell. Every single crystalline material you've ever seen is just one of these tiny blueprints, repeated millions and millions and millions of times in every direction.
Now here's where it gets interesting. That simple blueprint, that little unit cell, doesn't just come in one flavor. There are a few really important ways that atoms can decide to pack themselves inside that box. Two of the most common arrangements are body-centered cubic, or BCC, where you get an extra atom smack dab in the middle of the cube, and then there's face-centered cubic, or FCC, where you get an extra atom on the center of each of the cube's 6 faces. And these subtle little differences in packing, they completely change the material's properties, like its density and its strength.
I mean, this all seems incredibly organized, doesn't it? It can't be random. There have to be some kind of underlying rules that tell these atoms exactly how to arrange themselves into these perfect, repeating structures. And yeah, it turns out there are.
So how do they decide? How does a positively charged ion, what we call a cation, know exactly how many negatively charged ions or anions it should have as its neighbors? What are the rules of the game? Believe it or not, the answer is just beautifully simple. It all comes down to size. It's just a simple ratio. You take the radius of the smaller positive ion, and you divide it by the radius of the bigger negative ion. That's it. The number you get from that one little calculation predicts basically everything. It tells you the coordination number, which is just a fancy way of saying how many neighbors it can pack around itself, and the exact geometric shape they'll make. It is an unbelievably powerful tool for scientists.
Okay, let's do a quick example. Let's predict the structure of iron oxide, which is basically rust. So first, we find the radii. Iron is 0.077 nanometers, oxygen is 0.140. Step 2, we do the math. 0.077 divided by 0.140 equals 0.550. All right, now we check our table, and yep, 0.550 falls right into that octahedral range. So our conclusion? Iron oxide will have a coordination number of 6. And just like that, we've predicted that it's going to have the exact same crystal structure as regular old table salt. How cool is that?
So now that we know the secret rules, let's just take a quick tour through this incredible gallery of atomic architecture. Let's see some of the beautiful and varied designs that these atoms build for themselves. So on the left, you can see that rock salt structure we just predicted for iron oxide. But look at the one on the right, cesium chloride.
In that material, the ratio of the ion sizes is different, so it's forced to pack into a totally different shape. It has a coordination number of 8 instead of 6. It's a different blueprint, and that creates a fundamentally different material.
And trust me, the structures can get way more complex and beautiful. Take perovskite, for instance. Its unique layered structure gives it these mind-blowing electrical properties that are used in all sorts of modern tech. Then there's zinc blende, another totally unique atomic design. And every single one of these unique blueprints leads to unique, real-world powers.
All right, this is it. This is where it all comes together. We've seen the atomic blueprints. We've learned the rules of construction. So now, let's connect all of this invisible atomic architecture to the real-world technology that powers our lives. This is the part that shows why all of this really, really matters.
Okay, take a look at this. This is the complex blueprint for a class of materials called spinel ferrites. Now notice how some of the atoms are sitting in spots where they're surrounded by 4 neighbors. Those are called tetrahedral sites. And others are in spots with 6 neighbors, the octahedral sites. This incredibly specific, intricate arrangement is the secret to their famous magnetic properties.
And here it is. This is the big aha moment. By making tiny little tweaks to that same spinel structure, basically just deciding which type of metal atom goes into which position, we can create 2 completely different kinds of magnetic materials. On one hand, you get soft ferrites. We use those in transformers where you need magnetism to turn on and off easily. On the other hand, you get hard ferrites, which we use for permanent magnets and for storing data on old-school hard disks, where you need them to hold on to their magnetic information forever. Think about that. The same basic blueprint leads to totally different superpowers, all based on which atom sits where. So in the end, it really comes down to this idea, which the source material puts perfectly: it's not just about the chemical formula. The real secret, the magic, is in the relative sizes of the atoms and how that forces them to pack together in space. It's a story told not in chemistry, but in geometry.
And that leaves us with a pretty mind-bending final thought, doesn't it? If we understand these atomic blueprints so well that we can actually predict a material's properties just by looking at the size of its atoms, what's next? What new incredible materials could we start designing completely from scratch? What new superpowers could we engineer into existence just by drawing up a new atomic blueprint? The possibilities are absolutely staggering.